some information on which they can do criminals and shooters or terrorists. So low precision is okay. They are very well willing to go through a lot of data. And recall, well, if they get it, they really like it. But if they just get some information, it's also okay. There are also a lot of applications where you actually want to have high recall. So if you're talking about forensics or surveillance, or you're taking science of images, image collections as your research topic, then you really want to have everything that's in the database. You want to go through the whole database, categorize all the images in there, analyze all the images. You want to have very high recall. At the cost that you might have to go through a lot of data, which is not that precise. So you might take more time. Now, if you look at the methods that are available for those kind of things, you talk about automatic methods versus interactive methods, you will see that most of the methods that you look at are for web-based applications, but they must be automatic, because there's no one who goes to the first page after the first page of web results. Maybe you go to the second page, but interaction, almost nobody does that on the web. If you look at the other applications, there actually the standard is mostly interactive, maybe supported with some automatic methods, and combining the two, so interaction while also doing automation, is very, very rare. If you look at the intelligence kind of applications, then you're typically talking about some automatic filtering, because you have to find part of the data set you want to go through, and you do something like explorative search. So you're really going through the data set to find interesting parts of the data. That's what you're focusing on. It's interesting work there. I will not talk about that part, but I will talk about those applications where you want high recall, where you really want to go through the whole data set and have to analyze basically every image that is in there, or any video that is in there. So high recall retrieval. So what are the kind of processes that we envision when you're doing that? Well, one thing is you take any of your methods, any of your concepts, any of your metadata that's available, and you use that to sort the database. Get a kind of ranking, like you get in a web search engine, and then you start selecting the elements that are relevant to your task. We're trying to identify the most important ones. And then you assign them, you assign them to a category. Well, what are those categories that we're talking about? What can you have here? Well, it could be that is the category, well, I have my task, I'm looking, let's say I'm looking for terrorists in this large collection. So this is a terrorist in the category terrorist, and you're going like that. The second thing can be that you actually use the categories to throw away the information that you know that is not of interest. So again, assuming you're looking on the web for specific data, many of the web videos are completely irrelevant. So you want to throw them away as quickly as possible. So that could be a category, and something you don't see in most systems. It might also be that you're looking for subcategories. So assuming that your task is, I want to have, you are a biodiversity researcher, you want to find all the animals in this large collection. Well, finding the concept animal is maybe not an appropriate one, but it might help you to look for dog, if you look for cat, if you look for cow. So you look for different elements, different animals, and put them in different categories. And you start searching by this, and then the collection of your categories, that makes your final result. And we developed an application for this task, which we call the media table. This is a old version we have of that one. And it has a number of elements. So what you see here are typically between 40, 60, up to 100 columns. And each column is a concept. Each column is automatically derived the presence of people, the presence of a car, the presence of kind of standard settings like you see in all kind of papers, or all kind of presentations you've seen today. And they are the ones you can use for sorting. And when you sort them on, the whole database will be sorted according to this one little element. And then we have this part, that's where the buckets come in. So the idea that we have is you're kind of putting all those things in buckets. So this is the bucket for cars, this is the bucket for animals. So those are the categories that we're talking about. So a user is trying to put the relevant elements to the relevant buckets. And they are colored, so that you can actually see how they are colored in later, so you see what you are doing. And we have some things here, which is everything, buckets, those are the things, that's the whole collection. The things that you don't know yet, the ones that you have selected, the ones you have seen, those are the kind of elements that play a role in your categorization process. So, the final element you have there, scroll bar, well, doesn't actually show the whole collection, but it shows a bigger part of the collection, so that you get a feeling there are parts that I missed. I haven't looked at those, maybe I should consider whether there's something interesting there. And you see the gray values, you see that a value between 0 and 1 depicted as a gray value, and that helps you to find correlations. Because if you sort on one column and you see a certain distribution, and you see the same distribution in one of the other columns, there might be a relation between those two columns. And that is of interest in the beginning, but when you start looking at subsets, you can find very interesting things that you wouldn't see easily if you just look at the data. And we consider 3 interactive strategies to go through a database like this. For the first one, typical one, completely interactive. So you did some pre-processing before, computed automatic concepts, but then the whole idea of selecting elements, categorizing elements is just done by the user. So the user is putting elements into those buckets. That's the only thing that the system is supporting. That's one strategy. Second strategy is what we call manual relative feedback. So the user is still doing that, but when he has put information in one of the buckets, he can say, well, do you have more of this? So can you do automatic relative feedback, standard algorithm? Can you do that for this particular bucket? This is on demand. So the user is telling, now I want to have feedback, I want to use relative feedback to see whether I can find more interesting elements. And the final one, called unobtrusive relative feedback. Put everything in the buckets and then the system automatically tries to find information. Basically without you knowing it. You don't have to do something for it, the system will do it. Those are the 3 strategies that we consider. So, what is the idea? So those are the 3 strategies, how they go if you go from the whole data set. So in the first case, everything is uncategorized. You have to, your task is to categorize all of them. In a typical way, traditional video retrieval and the interactive, where the user is doing everything, you just have the whole collection, you find something, you put it in a bucket, you find something else, you put it in a bucket, and basically you have categorized in the end, you have found the elements for your task. That's one way of doing it. So the passive bucket-based retrieval, the manual bucket-based retrieval, you start with the whole data set, but now you're putting subcategories. So you're not only taking one task, but you're also putting elements in there which might be either completely irrelevant, so you can throw them away, or they are subcategories of the things that you're looking for. And by doing so, the elements become more consistent, they become visually more similar, so then feedback will also work better. So here the user can at a certain point say, well, this one seems like an interesting category, please give me more in this category. See whether in the data you can find elements which are similar to the ones that I already have. That's the second one. And the third one, you basically do the same thing, but every now and then the system tells you there is something of interest in your buckets. I found more elements which are similar to what you're looking for. You might consider this as being relevant. Those are the 3 strategies going to get buckets. So what's the overall system architecture? You have those buckets. And if the user is just doing the standard way of traditional retrieval, just interactive, you select the bucket, or you select a concept, you sort the buckets, you select items, you put elements in the buckets, and this is in a continuous loop. Well, you said you could do the same thing and say, well, if you have it, please give me more. Put the more interesting one, that's the one. And when the active buckets come in, the system is just looking at all the buckets. All the buckets go to this queue, and the system just selects a bucket from the queue and starts looking, are there any elements in my collection which might also be relevant if you find those relevant. Can you continue that process? And that's the loop that's up there. So the system starts going through all the buckets and see whether there's something interesting. Well, what does something interesting mean? How does the system get to those elements? it samples elements from the bucket as being, well, those are the positive ones. You sample other buckets, or basically the whole collection, just saying, well, those are negatives, those are probably not relevant. You train a new model, and based on the model, you determine whether there are sufficient number of elements which are relevant to the user. If so, if you found 5 elements which might be relevant, you feed them back to the system, or you feed them back to the interface, and the interface will show, okay, I have something new, maybe you should look at it. And the user looks at it and either uses it or ignores it. But the learning part is where we need to do something. So the bottom part. So we have 2 strategies there. We use the nearest mean algorithm, which is very fast, very simple, easy to compute. So you just compute the mean of the current elements in the bucket, and you rate the whole collection with respect to distance to this mean. Very simple classifier. You're not looking at negative elements, only at the positive elements. That's to be done very quick. More advanced method, using support vector machines. More expensive, but likely more accurate. I'll show how accurate they are. So you dynamically learn a new model from the examples in the bucket and the randomly selected assumed negatives, and you apply this model to the whole data set. And you see whether there are elements which are so similar that you want to use those. So this is the active buckets interface. I'm probably wondering, well, I've seen this one before. Yes, I've seen this one before. Because the only little difference is that here there's a little number, and it just tells, well, there are 12 relevant elements now. Those will just pop up. They don't need pop-ups. They just show that every time the user thinks, well, maybe there is something here. Of course, you can do some more highlighting, or but it turned out this was sufficient. So that's the only change in the interface that you will see. So what's the experimental setup that we use for this? We use the TrackFit 2008 data set. Most people are familiar with the TrackFit. For those people that are not. So this is a archive, well, it's coming from a archive actually in the Netherlands. That's a coincidence. Consisting of 200 hours of video, which is broadcast material. Things that have been broadcast in the Netherlands, has been stored in the archive, that has been made available to TrackFit. There are 35,000 individual shots, and for every shot you have a number of keyframes, so we are talking about quite a large data set. And we do 2 experiments. One, to determine whether actually it makes sense to use developers feedback in this data set, with exactly that we have. And a user experiment to see whether the 3 strategies actually work, whether they are valid ways of doing it. So, first thing we need is to analyze the data and have those concepts. Well, that is based on our medial engine, which we have been developing over the last 15 years almost. Which is a one pipeline, rather complex, but it is one of the best detection pipelines available. We tracked it, benchmarked, came out many times as top performer, or very close to it. And out of these elements from this pipeline, we have 57 concepts, which are things like cloud line, things like things like people marching, all kind of concepts which might be relevant to the task that you have. Those are the ones that have a reasonable accuracy. We used to have large 500, 600, 700, but many of them are not very high performance. Those are the ones that have typical good performance, so you can use them for research. Survey. So what are the tasks for evaluation? Well, we have 4 tasks. Data that we use. And the first one is to find pictures of Job Cohen, who at that time was the mayor of Amsterdam. And this is a type where you have a kind of very specific visual example. If you found that example, then you can find many more in the data set. Because they are visually very similar. There are a couple of clusters, but if you find those, you do very well. The second one is find both those ships in the data set. Much more variety, visually completely different, but advantage is there is actually a boat ship detector in our data set, in our concept set. So that might help in finding things. Manual finding close-up, hence, again, very high variety of results, both close-ups, further away, everything. Again, visually diverse, but there was a concept, hence, in our detector library. So that helps. Many black and white pictures of airplanes. There was no, clearly there was no one concept, airplanes in black and white pictures. So here you need to combine things, something like a black and white detector, an airplane detector. It's commonly known in the field. Combining elements is very difficult. Single concepts work quite well. Get combinations, I think, become more difficult. So the first experiment, to see the potential of relative feedback. Should we do it or not? So what we do, we 10 times take random selections out of the positive elements. So we take n positive elements 10 times. We learn using the two strategies. So the nearest mean classifier, which for this data set is something like half a second per bucket. Sport vector machines, between 2 and 6 seconds per bucket. And we just measure the number of new correct examples in the top 50 results. With the idea that a user is kind of willing to go through 2 pages of results, quickly see whether the results are actually good. And 2 to 6 seconds means that you can at least go from 10 buckets every minute. So that's, the system can do quite a lot. So those are box plots over the results. Here you have very limited number of examples, only 2. You see that you might have results. The difference between nearest mean and SPM is not that much. There's a small difference. If you go to more examples, if there are 5 examples, or if already 20 examples are present in the bucket, you see that if you look more and more at the green ones, you see that the SPM-based classifier actually works a lot better. So the more examples you have, the more it pays off to really learn this more expensive model. Then a user experiment. So we had 21 student users in 3 groups, one using the baseline, so only using interactive retrieval, no support by the system, except for just allocate concepts for the computer beforehand. So the passive buckets, so they could click on the button and say, now give me more results for this one. Or the active buckets, so the unobtrusive bucket expansion, and they had at most 5 minutes for each of the topics, each of the 4 tasks that were indicated. If you look at the number of elements found using those techniques, this is the result, baseline and then automatic, and there are 2 elements here. You should be able to get a star. So if you look at the significance at the 0.01 level, you see the manual performs better than the baseline in 3 out of 5 cases. And then the automatic method, so the unobtrusive method, in all cases was better than the baseline, so significantly better, but also better than the manual. So really the system was supporting the user in getting better results in a very unobtrusive way. And if you look at the elements there, it's kind of interesting that when there are elements where there's one concept available, then you see that the baseline is basically sufficient. So if you just find the right concept, you just go through and say yes, no, yes, no, yes, no. And the manual didn't help much. The automatic methods and the unobtrusive one still help in finding more and better results. So now if we look at the individual users, a very nice and complicated picture. What you see here is how when elements were found. So how many elements were found and when they were found, what the interactions the user had. If you see our little elements here, those were the points where the system or the user, depending on whether they're manual or active, were saying, okay, now I want to have more, now I want to have more, now I want to have more. So those were the elements there. Difficult to interpret all the different elements. Basically, it showed what we saw on the previous slide, that the green ones give the best result, then the manual ones and the baseline elements. Going into some deeper analysis, we covered the first task, which was a specific very specific tasks, find your coherent, visually similar elements. With the active buckets, the users were able to quickly say, okay, oh, I found it now, then you found one cluster, then you found the next one, then you found the next one. Very quickly you find the nice results. It was very good. So we just had a few results. Active buckets are there to help you in finding all the other elements. That was a very good one for active buckets. If you look at the second and the third task, so those elements were there, it was visually very diverse, but there was at least a concept available to start with. That makes the interactive retrieval easier. Just find the right concept, go through the list. That works quite well. So for the second task, active buckets, they had more results at once, but in total they kind of gave the same results. So the final result that they had was similar to manual interactive, but there were kind of larger hits and there were things found. If you look at the third one, so the difficult task of finding airplanes and black and white, the manually triggered expansion was very often wrong. So the user at some point thought, well, maybe this is a good point to look at things, and then the system just replied, well, there's nothing interesting here. So that was interesting. And what you see is that the manually triggered more, but the active buckets actually gave better results. They get more results in total. When task 4, the final one, sorry, this was the one where there was actually a concept. This was the one, this was a difficult one with having black and white and the airplane, and then it turns out that using two at the same time, two concepts at the same time, then interactive becomes very difficult. And when they had manual users make mistakes and active buckets were here. So high recall video retrieval basically requires an interactive approach. Fully automatic will just not work because it is too much. But active buckets are a mechanism to support users in an unobtrusive manner. So they don't have to do things instead of better results. Well, the SVM classifier gave the better results there. User experiments show that unobtrusive development's feedback actually gives better results. That's very nice. And they are especially suited when either there are visually similar clusters, which are the things when relative feedback always works better, or when it's difficult to find a clear starting point. So those two elements help you